So the main topic here would be to reuse logic of multiple network functions and network services in order to improve performance. So network functions, we used to call them middle boxes up until recently. These were all these boxes deployed somewhere in the network that provide services. It may be these services that you see on the screen, it may be other services. And they used to be monolithic closed black boxes provided by different vendors. We didn't know what's inside. We couldn't know what's inside exactly, at least. We couldn't see how they work, what the logic is. We couldn't configure almost anything. We had a very limited API for configuration, and that's it. And we used to just plug them in the network and hope they will work. They used to be or are still very high, with very high cost, very expensive, and they provide limited or no provisioning and scalability ability you have no ability to provision and scale because you have a box and it is capable of doing whatever it's capable, and that's it. If you want more, you have to buy another box. And as I said, it's expensive. So then came NFV that Danny already talked about a lot with the ideas of reducing cost and improving the provisioning and scalability by moving to software and virtual environments, virtual machines, containers, and so on. So we got reduced cost and improved provisioning and scalability, but of course at the cost of performance. And performance is a real issue here because these devices are expected to work in line rate. And so not only line rate, they are expected to provide low latency. So we can overcome the line rate problem by provisioning more instances and having a lot of servers. It might be even still cheaper than having these boxes and much more scalable or flexible. But latency is an issue, a real issue, because even if you scale as many as you want, latency would still be an issue because it's software and not hardware. So another problem we had with this, all these devices, which stays even after this NFV idea came into our minds, is the limited and separate management of each such function. So each function has its own API, its own CLI, configuration, management interface, and so on. And in order to manage them, you have to understand how to manage each one of them separately. And so you have different vendors with no standards. And the reason is that each one of them has a separate control plane and very different control plane. But actually, if we will look inside these boxes, if we were able to, and we are able to some extent, now that they become software, it's much easier. We see that inside they're somewhat even very modular. And when I say modular, I mean they're built on known building blocks of known algorithmics for classification, for packet handling, and all this stuff, which is widely known at least in the research community, also in the industry. But still, we have very limited functionality on this box. We're limited to functionality given by the vendor, and we are limited in the innovation. Let's say a box uses a specific certain algorithm, but we want to use a different algorithm because our workloads much better the different algorithm. We can't just go into the box and change this module, keeping all the rest like the same, and have better performance. The only way, given these black boxes, is just to build a new box. Also, what we can see is that multiple very different boxes use similar processing steps, similar modules, but there is no reuse across them. And sometimes, and we show this in this work, sometimes these processing steps can be reused to reduce the amount of computation, to reduce the processing performed on a single packet, for example. And by that, for example, it can reduce the latency, the overall latency that the packet is exposed to when it passes through a chain of such network functions. So we presented in last SIGCOMM, we presented OpenBox. It's a software-defined framework for network function. And the idea in OpenBox was to decouple the control plane of network functions from the data plane, very similarly to OpenFlow in the forwarding domain. Here we try to do that for network functions in more general way. So instead of having a control plane on each one of these network functions, we wanted to have a controller that holds all the logic of the control logic of all applications. And then instead of having these applications scattered around the network, we have in the network some general purpose, let's call them like that for now, boxes that can perform the logic of any given application, to be very simplistic. So the benefit we get with that is easier and unified control, better performance, and especially improved latency, and I'll show you soon how, scalability and flexible deployment, isolation between tenants, and it allows innovation by the definition of this framework. And just to make the comparison to SDN, so we had all these problems of high cost and limited scalability and provisioning and management and functionality and innovation and complex processing and all this stuff in middle boxes. But before that, we had that in switches as well. The idea there was, and the reason for that was the separate control plane and different control planes. And the idea in SDN was very similar to unify the control plane of these switches into a software controller running, for example, OpenFlow, communicating using OpenFlow to these switches. But we know from studies that about 50% of the appliances in a network are not switches and routers, are not used for forwarding. They're used for other purposes, all these other purposes. So handling only the switches and routers is not enough. Yeah.
Yeah. Question is, so what's the required latency between the decoupled data plane and the control plane?
Sorry?
What's the required latency? What's the
required latency between the control and the data? This is relatively low because, and it depends on the protocol and on the applications. But what we try to do is that the control plane is not changing the data plane so much during runtime. It defines the data plane, but it doesn't change it like on a very frequent basis.
So for the state information is still in the data plane,
yes.
Not in the control plane?
Yes.
Okay.
So this is how the framework looks like. We have, I'll go from bottom to top. We have these service instances, these general purpose boxes that actually apply the operations on packets, on the, every packet and packet flow through these boxes, one or more of them, and continue in the network. The packet never go to the control plane. In the control plane, we have a controller that communicates using a protocol we defined with these boxes and define their logic, the processing that they're doing. And on top of that controller, we have an API to program applications, which are network functions in fact. But now these network functions are being realized using this service in the network. So, yeah. So additionally, it gives the isolation I told you about, and it has support for hardware accelerators. I will try to talk about this as well. And you can dynamically extend this protocol. It is not set to specific tasks. You can add tasks, you can add building blocks to the protocol, and by that create virtually any network function you would like to have.
So the API and the protocol you define? Or?
Yes. But it's completely extensible. So the basic observation we started with was that most network functions do very similar processing steps in general. But there is no reuse between them. That's what we based our design on. And I'll give you some examples. So if you have a firewall and you open it up and look inside what it does, it's a very simple firewall for this example. What you will see is that it reads packets from some network interface, then it classifies them based on some fields in the header, for example, and decides whether to drop a packet, to report it to some administrator or so, to log it maybe, I don't know, or to just output it untouched to the other interface. Now, load balancer, completely different purpose, but as you may see, somewhat similar because it reads packet. Based on the header fields, it does some classification and decides whether to modify the packet or to just output it, or maybe output it to a different output port if it has multiple, and so on. And you can look at somewhat more complex network functions like intrusion prevention system. It performs classification based on the header, then it performs classification based on content of the packets, deep packet inspection. And then it may drop the packet or send some alert, and it may have multiple DPI engines and so on. It might be more complex, but still, you can still model it somewhat this way. So, yeah?
On the more conceptual level, but the first two functions also happen in the switch and in OpenFlow, so why not unify it all together with?
It's possible. It's possible to unify it with OpenFlow to some extent. I may have time to talk about it at the end. But OpenFlow is very limited. But of course, you can do all of the, you have switches that do intrusion prevention system as well. But this is up to the manufacturer to provide you these specific abilities in the switch or not. OpenFlow doesn't give you DPI, for example.
Yeah.
So, yeah. But, and you, of course, can have much more complex firewalls and load balancers as well, with state and so on. So this you can't do in OpenFlow.
This is why I asked on the conceptual level. You
Yeah.
think that's the right thing to separate it completely, the box, let's say, of the forwarding, then the box of the open box of...
I don't think it should be completely separate. I think there will be some level of separation because of the will to keep the forwarding plane as simple as possible, which has some it somewhat makes sense to keep it simple, and here it is not simple anymore because you want as flexible a framework that is as flexible as possible. But you can use the forwarding plane also to provide some of the mechanisms or behaviors that you would like to provide to these functions. I will try to get to it. So we have this node mode API, and the API is actually an API to define these graphs. So if you develop some network function, you actually, in our system, you create a graph. You define each block in this graph. Each block has a configuration. It might be a complex configuration. You define the relationship between blocks, the edges of the graph, and you give it through this node bound API to the controller. The controller then has a mechanism to merge these graphs. I will talk about it soon. And the controller also returns information to the applications. The application is all these graph settings, which may be multiple graphs per application. It depends on what the application does. And the event handlers. So the application can request to know about specific events in the network, and it can also request to receive information of load, for example, in specific service instances and so on. So this goes up from the controller to the applications. Then we can have multiple tenants running multiple applications for multiple different policies in the same network. And we have isolation by the definition of this API, because if it is a declarative API, each application cannot query anything about other applications. So we have isolation between the application and tenants enforced by the API itself. Then we can connect to an SDN controller, and it's for your question, and have some kind of network-wide view, not only of the network functions, but also on packet flow and traffic in the network, and also control scaling, provisioning, placement, and so on. We do not touch it in our work, but it's possible to have this information from the SDN controller if it exists, and then have a much more complete system. Now, what a controller does. So one major part of the role of the controller is to receive multiple graphs and decide how to execute them in the data plane. Now, it might be that we have to, we want or have to execute multiple functions on the same data plane location. Maybe because packets go through both functions, and we want packets to go through a single virtual machine instead of multiple, or a single device instead of multiple. Or it just makes sense for other reasons. let's say we have two graphs of two network functions. Here it would be a firewall and the intrusion prevention system. And we would like to have a box that performs both of them. We can naturally just concatenate the graphs so that we have some kind of this graph. This is the logic of the firewall up until here. We don't have to output it to an interface. We just continue with the logic of the IPS. When we're done, we send the packet out. But this, well, it's better than having two virtual machines and bouncing the packet between them. But still, we can do better. So here is the interesting theoretical problem here. How to do it better? Yeah, if we can also measure the time that it takes. What's interesting in the graph is the diameter. And more precisely, the number of classifiers in the diameter, because classifiers, in most of the cases, classifiers are the ones that take most of the time in computation.
So DPI is also unified as classifier?
Yes, because it classifies the packet based on the content of the packet. Yeah. So we would like to narrow this diameter. And when you see this icon, it means a problem that you can take home and think about, and I'll be happy to discuss. We have this input. This is the input of the problem, these two graphs. How can we make it a single graph with the shorter diameter? This is the algorithm we presented in the paper. It's some kind of a greedy algorithm, very simple, just to show that it's possible. It might have some cases of when it is not very efficient, I know. But just to show you the maybe the naive solution, but still not concatenation. So what we would like is to reduce the number of classifiers. So first of all, we normalize the graphs to a tree. Yeah, I know that. So the graph is directed acyclic, but and I know it is true that in some cases this can be brought to exponential number of nodes in the graph. But in all the cases we tried to look at, it never happened because to get to exponential number of nodes, you really need a specific characteristic of the graph, and in my opinion, you'll never have it in a graph of network function. But if you have it, then this algorithm is not the right choice. So we normalize the graphs to trees, and then we concatenate them. So at every point, every output point of this first graph, we replace with the first point after the input point of the second graph. So we get this graph. Okay, this is the firewall, and from here it is the IPS, and also here it's another IPS, just pasted instead of the output block of the firewall. Now we're looking at the paths from the beginning to end, and specifically we look for two classifiers of the same type on the same path. So we find this path, and we can actually take the two classifiers, take the Cartesian product of both classifiers, of both tables, and create a new classifier instead of them. We argue that this Cartesian product will be small. If it's not small, then it's a problem again. But in most cases, it will be very small because it does not. The intersection is very small. Here again, we have a path with two classifiers of the same type. So, but we have some block in between. So the question is whether we can move this block to be after the merged classifier or not. In this case, it only sends an alert to the administrator or to the controller. So we can move the alert sending to be after the classifier. But if it is, for example, change the packets, then it might be a more interesting question whether the packet change is related to the header, to what the header classifier is looking at or not, and then decide. In our initial implementation, if we see a block that modifies packet, we just prevent, we avoid the merge. But here we can do that. So we end up with this single header classifier that does the classification for everything. And because of that, we need to duplicate this block multiple times. But now the last stage of this algorithm is to take all the redundant blocks there is a very simple way to find them, and just remove them and rewire the arrows accordingly. So we get this graph. And the diameter of this graph is shorter. And this was a very simple example. We just removed one classifier, and we got an improvement in performance of about 22% in the latency. When it is not good to merge, I'll skip it, but when the cross product is too big, we found in our data sets it never happened, but it's possible theoretically that it will happen. And also, when you have a classifier that most of the data would not go to the second classifier because most of the traffic doesn't follow the rule that in this classifier that send it to this classifier, then you may not want to have a huge classifier here, and you want to avoid this merge. So we may have multiple, many blocks, such blocks, these cubes in the graphs, and we try to model very many different blocks that are used in network functions in order to model as many network functions as we can. And we implemented this service instance that provide all these services, all these processing blocks. Yeah.
Just a comment about what you said before. You said that you don't want to merge them if you have most of the traffic is going to let's say the legitimate traffic.
Yeah.
But this says also that probably your measure is not the right measure because you are now looking at diameter. Probably you have to look at expected diameter or expected path rather than diameter.
Yeah, you're right. But then you have to know something about the probabilities.
You know that 90% of your traffic.
So in our system, we didn't have any mechanism to measure the network and understand these traffic matrices that could give us this expected diameter and so on. But you're right, you will have to have that in order to do this avoidance.
Avoidance, and also then change your measure, change your objective function, because the objective function should not be the diameter.
Yeah.
Because if the diameter is only 1 in a million, then what do you care if the diameter is large?
Yeah. So, as I said before, the algorithm I just presented, it doesn't really care about the diameter. It just tries to merge as many classifiers as it can. It's not like an optimization problem.
No, but this may be bad because it may make the expected diameter worse.
You're right. Yeah, you're right in these cases. Yeah. Yeah, so this work was mostly building the system and defining it, not finding the best algorithm for that, and I know that. That's maybe why I came to present it. So I just think that it's very hard to model this problem for as an optimization problem. I'll be happy to do that, but it's not easy. So another thing that you can have is you can have the data plane distributed in this framework so that you have multiple service instances, and packet would go through more than a single service instance, and it might be that some service instances are implemented using hardware, some software, and there is a mechanism to attach metadata to the packet from one service instance to another to make the state flow between them. It uses well. This gives you another opportunity for performance optimization as well. That's the open part here. When you can split the graph and not merge it. Instead of merging it, you can think about splitting the graph and what is the optimal splitting for a graph given some information on each instance that the packet would go through. And how many instances you would like the packet to go through. There are all these questions. So I'll skip it. Yeah, the data plane is also extensible. You can add modules to the data plane and add applications that use these new modules. I won't get into it due to time constraints. This is on scalability. Well, it's less important. Okay, the protocol defines these blocks that you can also add additional blocks, but in the service instances can provide different implementations to these blocks. And this can be taken into account in the controller as well to make the model more complex. So The service instance sends a message to the controller when it comes up. It's like an hello message. And it says, I support header classifier block that you may want to use. I have multiple implementations for it, and it might even specify some information on these implementations so that the controller can say, okay, I give you a graph now, but you use this specific implementation that you have for this header classification part of this graph, and not this other specific implementation that you may have, because I want this and that behavior or characteristics of this block. Now, this can, of course, affect the performance, and that's why the controller may need to be able to know something about it and take it into account. For future work would be to, that I'm thinking about is to design some system that defines not only, well, this is what everything I just showed is some kind of a clean slate solution for all these problems. But you may think about a gradual solution where you have already OpenFlow and SDN, for example. You have hypervisors. You may have hardware accelerators in the hypervisors or in the infrastructure. And you would like to give the network functions the ability to offload some of their operations to this infrastructure, to the network, to the switch, to the hypervisor, and so on, to the virtual switch, and so on. And by that, you can you gain the reuse for these offloaded tasks, because the offloading, the infrastructure that provides the offloading can then do this merging and decide whether to reuse the same service for same instance of the service for multiple different network functions. And you also gain, you may gain improvement in latency, because a packet would go through less processing in the network function and more in the infrastructure. So the challenge here is to design a system of protocol that allows this. This is how it may look in my mind, but I won't get into the details. We implemented that. I'll just show some results of performance. So if we had packets that go through a service chain of firewall and IPS, for example, and the IPS performance is here. The throughput is low, the latency is very high, and the firewall, the throughput is higher than the IPS, and latency is lower. But so if we had them just flow this way through different VMs or so, without our system, they will have the throughput of the IPS, because it's the bottleneck, and the latency of both of them. Using the system, you can have these two VMs act as our service instance and run a merge graph of both of them. And then a packet would go through a single VM now for all the logic, and you will get the throughput will be higher because you have two machines running, and the latency will be lower because it traverses only one machine. It's a bit higher than the latency of the firewall here, but just a little bit, because the graph is a bit more complex. So that's the improvement. That's really work. Yeah, so this summary, network functions are a real challenge, as Danny already said, and this latency issue is very bothering. I know that in VMware as well. And this decoupling of control plane and processing and data plane processing provides all these benefits, but there is still work to do to make it really optimal or closer to optimal. So I'll be happy to hear your inputs later as well. Thank you.
If we have this protocol, do we still need OpenFlow?
Yes, because OpenFlow is for forwarding devices, and you probably don't want all your forwarding devices to speak this protocol, because it's much more complex than OpenFlow, because it's much more flexible. So I still that OpenFlow or SDN-like protocols are still needed for specific forwarding devices. You can, I think you can achieve most of the basic OpenFlow behavior using this protocol. So you may have a device that only provides this part of the protocol, because service instance in our framework doesn't have to provide all the required behaviors. Like it can only say, I only support this specific block and that's it. So, and it's fine. But, so maybe this can replace OpenFlow in this sense. But OpenFlow is much more tailored to forwarding devices. So I won't say it's useless giving this protocol. Yep.
Have you looked at implementing any of this on P4?
Well, you can use P4 for implementing only a very small part of it, almost just as OpenFlow. Like you can implement classifiers of some kind of header and maybe look somewhat into the packet for a fixed length and so on using P4, but not much more than that. So I had a slide I removed for lack of time, but we thought about having our implementation that I skipped here. We have this is the data plane implementation of our code, and we have we have some code in Python that communicates with the controller, and then we have a translation engine that translates the graphs given by the controller to whatever you would like, and you can change this translation engine. We translate it to click specifically, but you can change it to retranslate it to P4 language, and by that have some P4 switch somewhere where the packets flow through. So yes, you can do that. Okay, thanks.